But how can this be secure?
I guess he runs everything inside sandboxes.
Claudio! Ready to go.
I guess we need good predictions here. Left or to the right?
The right?
Yeah, let's try that. Oh, here he is! Claudio! On your test system, you run everything inside sandboxes, right?
Even better, I run everything, all student code runs in its own virtual machine, so you cannot break out of that.
Oh, wow.
Tunnels are everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coughing just a bit in bridge, you start tunnels for fun and for the prize, cause tunnels are with us all the time.
Wait, Daniel, I mentioned sandboxes and virtual machines there. We didn't even explain them, right?
But what do you want to explain there?
I mean, they know processes already. They are just instances of programs running under the same operating system kernel.
And they cannot access kernel functions, physical memory, or devices directly.
Yeah, that's right. They need to use the system call interface. It's like an API. It just provides a safe interface to the kernel that allows you to request things to be done.
And sandboxes? Sandboxes basically isolate a group of processes by changing their root, for instance.
By hooking in the system calls.
Oh yeah, you're right.
Yeah.
So inside a sandbox, it looks like that the directory it's running in is the actual root directory of the whole system.
Exactly.
Well, I think we should highlight that here. Sandboxes usually use kernel features, and that means that all sandboxes share the same system, so they share the same kernel.
That's a difference to virtual machines, right?
Yeah, I mean, virtual machines, you have different operating systems that running in there. You don't share the same kernel. It's just you emulate a whole system for a guest.
Yeah, that's right, yeah.
And that's implemented in software, right? So in the most simple case, it's like an emulator, emulating the hardware. But in a more advanced case, it's like hardware supported stuff, right? Like into virtualization extensions.
Yeah, but in this case, we don't call it like an emulator. We call it a hypervisor.
Hypervisor? That's a strange name. Where does it come from?
That's actually something, a word that is much, much older than we are. That's from the 1970s. So in a typical system, you have user mode and you have the kernel mode, or you could also call it supervisor mode. But who supervises the supervisor? The hypervisor.
Okay, but that's basically it, right? So they know everything about sandboxes and virtual machines, right?
Exactly.
But wait a second. Didn't they already use sandboxes for their exercises?
So if it's a virtual machine, you cannot really escape it.
Why not? Can't you just run an exploit?
Yeah, if it would be like a sandbox, you could run an exploit on it.
But the hypervisor is a piece of software.
Yeah, you're right.
And every software has bugs.
All software has bugs. And all hardware has bugs, because we write hardware the same way we write software.
Look, there are exploits for hypervisors.
Oh, wow.
Oh, Claudio, one quick question. How sure are you that one cannot escape your virtual machines in a test system?
I'm entirely sure. It's like 100% sure. What? Nothing is ever 100% secure. No way I'm saying that. I'm rather confident, but same as for every system. If you search long enough for something, you find something.
And it would be good to know if there's a bug, right?
I mean, of course, and feel free to search for it, but same as the last time. If you find something, like exploiting vulnerability, please let me know.
Yeah, of course. Of course. Thanks. That's odd. So I have a hypervisor here, an old version, and an exploit for it.
Are you trying to...
No. I'm just pen testing Claudio's test.
And he knows about the...
Yes. He asked me to tell him if there are any bugs.
Okay, well, yeah, let's have a look. So the exploit script there, you pass a fixed address here. So you assume that You have no ASLR? Does Claudio use ASLR?
What was ASLR again?
You have address spaces per process, and also one for the kernel. And you can place things at different offsets in these address spaces: code, data, heap, the stack.
So this will of course interfere with my exploit, because it assumes to have a function at the specific address and probably cannot find it.
But maybe you can break ASLR.
You can break ASLR?
No idea, let's ask Google.
Yeah.
Break ASLR. Here, Kane, silently breaking ASLR in the cloud.
We don't have a cloud, but virtual machines, so this should work.
So let me take a look. So we have here... Oh, wait. It requires memory deduplication.
I don't use page deduplication. Use something else.
Maybe in the next one. ASLR on the line. Practical cache attacks on the MMU.
Sounds good, but I'm not sure if it applies to virtual machines.
Yeah, I'm also not sure. So maybe let's try another one. NetSpectre?
So why don't they use NetSpectre? I mean, come on, it's a great paper, but probably it's not suitable there.
Yeah. Let me change the query here a bit. We don't want to break kernel ASLR, but hypervisor ASLR. Here, this one, proof of concept for breaking hypervisor ASLR using branch target buffer collisions.
Perfect! And this attack exploits the branch target buffer, which is a part of the branch predictor.
Wait, a branch predictor? Shouldn't computers be deterministic?
They are deterministic.
But why predictor then?
Well, you sometimes need to...
Wait a second. Try this for a second.
Huh?
This is just a loading program.
What is going on now?
I thought it could be useful to have this kind of setting to explain some more technical stuff. Okay. Can I load a PDF or something? Of a processor pipeline, maybe?
Whoa, I think that's the wrong avatar. Oh, where's my body? Oh, yeah, okay, I'm here.
Processor pipelines today are quite complex. If you take a look at this, so in the beginning, when you want to run a single instruction, you first have to fetch it, then you have to decode it, and afterwards you can execute it, and the result, you have to write the result back to memory.
Yeah, but doing all those things after each other is really slow. This is why processors pipeline them.
Yeah, exactly. And so if you take a look at this one instruction here that is executed, another instruction might already be decoded while this instruction is executed.
And this means that all 4 stages run all the time in parallel.
Yes, and that's efficient, but you might start fetching an instruction before you even know whether you should be executing it, because the previous execution phase has not finished yet, and that could be a branch decision.
Oh, and that means if the branch jumps somewhere else, the whole pipeline has to be stalled, everything that's already in the pipeline has to be flushed, and only then you can start fetching the next instruction.
Yeah, that's called a pipeline hazard. And that's where branch predictors can really, really help.
I never really thought about how they work, but if I don't have any branch prediction, am I also not also predicting that the branch is always taken? So it should be right 50% of the time?
Yeah, that's true. But that would be a very dumb predictor, right?
Yeah.
So take a look at this very simple code example here. So in this example, your predictor would be mispredicting every single time we run through this loop.
Oh, yeah. Wait, but I have an idea. What if I use a cache and it stores for the address of this branch if it was taken the last time or not?
Ah, yeah, for this example.
It works great.
Yeah. And that's basically a single bit that you store there.
Yeah.
A single bit. Let me maybe modify my loop just a bit. So like this. What would you say now?
Oh. Yeah, so here the prediction is always wrong because it changes with every loop.
Exactly.
So, but what if I take a counter? Counting from 0, strongly not taken, to 3, strongly taken. And whenever a branch is taken or not, I move the counter in this direction.
Yeah. That sounds like a very clever idea. But what about this?
Yeah.
The branch predictor will now always switch between the middle two states. And that's pretty bad.
Yeah.
Right? Because every single branch would be mispredicted again. So the question is, what can we do here? And that's where the pattern history table comes in.
What's that?
Your idea was to just use the branch address as input for the prediction. So you predicted based on the branch address, should this branch be taken or not?
Right.
But you could do more. You could use information from the past, from the history, and use that to predict the future. The principle of locality again. So what we can do here is we could take, for instance, the outcome of the last 2 branches, like this.
But then I need 4 counters, right?
Exactly. Now you need 4 of these counters. And then you can take the history into account. And let's take a look at the code example here.
Yeah.
And here you can see
it now works every time. Like the prediction is correct every time.
For this example.
Yeah, of course.
These 2-level branch predictors, they are very common in practice. So they are widely used. But that's direct branches, right? What if I add indirect branches? So in this case, you cannot do everything with a counter. You maybe have to add something more.
Yeah. Let's add another cache.
Another cache?
That stores for the source address, where the branch is, the target address, where it jumps to if it is taken.
Okay, a cache that stores the target address. Yeah. This is what we commonly call a branch target buffer.
Yeah.
Which does exactly that. And if you take a look at this code now, this is fine. But what if I add the alternating pattern again?
It just gets more and more complicated.
Yeah, you probably then have to combine all the techniques.
Yeah.
Manuel, are you still there?
Yeah.
Can you show us a different PDF? I want to see a branch predictor on an Intel Haswell processor.
You could do such nice stuff with a VR headset and you are watching PDFs.
So it's basically, as you said, it just gets a bit more complicated. So we have here our taken branches, right? And they are then provided as input. They are XORed together. The source destination information is XORed together. You have the branch history buffer that is then used like the pattern history table. And then we also have the part with the branch target buffer to predict the branch targets then. So basically everything that we mentioned is in there. It's just a bit more complicated, a bit larger structured.
Yeah, of course. Yeah, interesting. But how do we exploit that?
Guys, come on. You can watch PDFs
Daniel?
on laptops. You don't need
Daniel?
a headset for that.
So have you checked out the Hypervisor ASLR break yet?
You mean the paper by F. Dushkin et al.?
The jump over ASLR?
Yeah. In this paper, they found that only the lowest 31 bits of the branch address are used index in the PTP.
But the BTB doesn't have 2 to the 31 entries, right? So it is organized like a cache, I think, with some index, a tag, and data.
But the data is the branch target, so an address to jump to.
Yeah. So how do they use that to break ASLR?
Well, let's say you have several processors with a branch at the same virtual address.
Yeah. And then?
You see mispredictions if they run on the same core.
Oh.
Actually, that is already patched by the Spectre patches.
Yeah, at least partially. I mean, I would not rely on that. I'm sure there are some CPUs where you could still run an attack. But if you want to attack the kernel, you need the same virtual address, right? For the kernel, that should be difficult.
Not really, because the BTB uses only a few address bits to index the address set. So there are collisions.
So how many sets and ways are there in this BTB cache thing?
So finding out how many ways is easy. Just start programs with branches at the same virtual address, and as soon as you start seeing mispredictions, you know how many ways there are.
Yeah, that makes sense.
And on Haswell, for example, that's 4.
That's from Matt Goldbart's blog, right?
Yeah, right. Yeah. Okay, and the sets?
For the sets, that's also quite easy. So you just add branches at different locations, and when you have added enough branches, you see the mispredictions going up a lot, and then you know how many sets there are.
It's like cache lines, basically. And in the BTB, this would be the BTB entries. And how many of those are there?
4,096.
4,096. And we had 4 ways. That means there should be 1,024 sets.
Yes.
Yeah. And if you know where the branch is, then you know where the code is, and that means you broke ASLR.
Exactly. Because the kernel has branches at randomized offsets. Yeah.
So did I get that right? You create a program with branches that map into the same BTB entry, and this BTB set, is the one that also a specific kernel branch uses. And when you then run these branches in a system call that triggers this kernel part alternatingly, then you would see mispredictions and you could tell whether you guessed the branch location correctly.
Yes.
Wait, for a hypervisor, that's even easier, because the operating system running in the virtual machine fully controls all the virtual addresses. You can just set up, map virtual addresses as you like and jump around there as you like. And it could be the same virtual addresses the hypervisor uses.
Yes. I will try that now. It works. I got the ASLR offset.
Oh, so your exploit, can you run this?
Oh, it also works now. Claudio? And now I have code execution in your hypervisor.
Code execution in hypervisor?
Yes.
That means you can run any code with the rights of the hypervisor.
Yes. Look at that.
I guess I need to mitigate that.
But that will not be so easy. This is a problem in hardware.
I mean, can't it disable that?
The branch predictor? Have fun. You can disable it, but I mean, how slow and inefficient should your computer become?
You could just flush the branch predictor upon every context switch.
But that's just as efficient as disabling it.
Almost. It would be a bit better, because you would still build up predictions while running between those interruptions.
Isn't that what the Spectre mitigations actually do?
I mean, they have different mechanisms for that. One of them is called like indirect branch prediction barrier.
Yeah, IBPB. And it's sort of like a BTB flush instruction.
Wait, you broke KSLR. How much randomization is there really?
Linux KVM only randomizes the middle 10 bits of the virtual address.
That means I could also just guess the address, and if my guess is correct, the attack works?
Yeah. I mean, any attack should work with ASLR that works without ASLR. ASLR just randomizes things.
But then ASLR is completely useless.
Well, it makes things less convenient for the attacker. Yeah?
Okay, I give you that, but that's a secondary issue, right? I mean, the primary issue is still...
The exploit. The exploit only works in old KVM versions.
But why do they use the old version?
I don't know.
So that we have a nice setup for the episode.
So the students have to implement an attack on the branch predictor now?
Well, they can if they want, but I have a better plan for the next episode.
Okay, now it should be updated. For some reason, unattended upgrades were disabled.
Guys, so I have this problem with my laptop. You know, I'm trying to install some software, and can you help me, guys? Please?